So a moment's question, you've got a plank resting on these two chair backs, and you can obviously assume that the chairs aren't going to fall over inwards. Just pause the video if you need to and just make sure you've read the question carefully. Now, a separate diagram is recommended. So you've been given a picture. This is a picture. You need a force diagram. Now, you might also need a resolved force diagram for some questions, but not this one, because all these forces are up and down. So you've got the weight 10g of the plank right in the middle, because we're assuming that this is a uniform plank. And to counter that downward force, there are reactionary forces at A and B. So let's just stick on some lengths. Now, resolving vertically, we can simply say that RA plus RB is 10g. That doesn't allow us to work out either of the individual reactions, but it does give us a relationship between the two reactions. We can't resolve horizontally because there are no horizontal forces to worry about here, but we can take moments. Now, you can either take moments about point A, or point B, or the centre of the plank, or frankly any part of the plank that you want. You might even do the far left point. You might do a point 2 metres in from the left. It doesn't matter. Because this plank is in equilibrium, then there should be zero total moment about all points on the plank. So the simplest point to pick is either point A or point B, because of course it helps to eliminate one of the forces. Watch. If I take moments around point A, I first get some, I'm standing here looking out this way. This force here has zero distance from the point I'm taking moments around, so we ignore it altogether. That's what I mean by eliminate a force, by choosing a point around which to take moments. The 10g force is 3 metres away, and that's turning round this way, so it's clockwise, so positive. The RB force is pushing anti-clockwise, so it'll be negative, and that's 7 metres away. And the plank is in equilibrium, so total moment is 0. Now, rearrange that and you get out RB as 42 newtons, and that allows us to work out RA using this formula as 56 newtons. So to answer the question, the chairs will break if there's a 50 newton force or more, so of course the chair A is going to break. Okay, the next one looks like this. You've got a shop sign. Again, pause the video, just have a little read. You've got this shop sign, which is not a wire, it's a lamina. Actually, it does say actually down here, it says a uniform lamina. Now, you've got weight 40 newtons. Now, because it's a uniform lamina, that weight is going to act from the centre of the sign downwards. So I'm going to draw that on there, 40. Now, to deal with moments, you're going to have to put some lengths on here. So we've got 0.25 of a metre. If you read the numbers down here, you spot that you can quickly put on these numbers. Notice I've extended the line of action of this force, because I'm going to need to know that in a minute. And 0.4 is the height. Now, resolving vertically again should be the first thing you do every time. We get T1, there's only one force up and there's only one force down, so they must be equal. T1 equals 40 newtons, so we know that straight away. Resolving horizontally, T3 must equal T2. And then, again, we need a third equation to be able to work out T2 or T3, and that involves taking moments. I'm going to take moments about point A, because doing so will eliminate these two forces, because they will have zero distance from A. Their lines of action are 0 centimetres from A. And it will just be about these two forces then. So moments about A. Clockwise, we've got 40 times 0.25. Anti-clockwise, we've got t3 times 0.4, and again the sign is in equilibrium, so 0 moment. Rearrange that, we get t3, and of course we know that t2 is equal to t3. Okay, the last example for now is this one here. Pause the video. Okay, there's a lot to read here, and also the picture they've given us is really unhelpful, because they've told us that this 20 Newton force is x centimetres away from A. So it's not necessarily in the middle. And in fact, because we've got the weight to draw on, we want to be able to draw the weight in the middle, and therefore this 20 Newton force should not be drawn in the middle, because it's not very helpful to have it there. So the picture's rubbish, so draw a separate diagram. I've highlighted that it's a uniform rectangular lamina to remind you that the weight will act from the centre of the rectangle. So here's my version of the diagram. I've indicated point D on there. I'm going to start putting some forces on. There's the weight, 80 newtons, and I've extended that line of action upwards because I'm probably going to be taking moments about D. We've got this 130 newton force to the right, and we've got this 20 newton force pointing down. Now we can draw that anywhere we like on the base, pointing down, and we just need to indicate how far it is from A. So X, we've got 15, and the 2 10s there as well. So I think that's a complete diagram, really. Or is it? Because if we were to resolve vertically now, what's going to happen? We've got 20 newton force down, we've got an 80 newton force down, so we've got 100 newtons pulling down. Well, at the moment, the sign is going to just accelerate downwards, isn't it? And similarly, we've got 130 newtons pulling to the right, so the sign's just going to go whizzing off this way, down towards the ground, down there. It's not very helpful. That's probably not what's happening. And of course, it's not going to happen because we're told that the sign is attached to a fixed bolt at point D. So what must be happening at D? Well, there must be some forces there to counter the other forces. Now, to answer this question, you don't need to know about those forces, but I can guarantee if this were an exam question, you would, or there'd be a part B where you would need to look at the forces acting by the hinge on the lamina. So my recommendation to you is whatever the question is asking you is to do a complete force diagram every single time, with all the forces you can find. So I've called them capital X and capital Y. I probably shouldn't have used an X because I've used an X here, but I have used a lowercase here and a capital here. So we're ready now to do all the equations. Remember, once you've got a good force diagram, it's easy then, it's just equations. So resolve vertically, and we get y equals 100. Resolve horizontally, we get x equals 130. And then we can take moments. Where to take moments about? Well, the sensible place is about point D because it eliminates these two forces, and we're not actually interested in those two forces, especially because we already know what they are. So, moments around D, clockwise. We've got 20, which is x centimetres away. If we extend that line of action from the 20 up, like we've done with the 80, we can see that the horizontal distance, therefore, would be x centimetres. The 80 is 15 away, and pulling round to the left, if you imagine just 130 is going to have a sort of anti-clockwise pull on the sign. So subtract 130 times 10. It's 10 away, isn't it? Perpendicularly. And again, the sign's in equilibrium, says it there. So equals 0. You rearrange that and you get x. Comes out to be 5 centimetres.